Awesome.
So we begin?
Yep, sounds great.
Okay. All right. So yeah, as I was saying, I wanted to discuss Cauchy's functional equation today, and after a little time, do some questions about Cauchy's functional equation as well as monotonicity. Yeah, so if you're not familiar, this is Cauchy's functional equation, right? It's asking you to find functions which are additive, which means they commute with addition. And in this case, we're looking for functions from the real numbers to the real numbers. Now, there's an obvious class of solutions that you have for Cauchy's functional equation. But of course, f of x equals x works. And if you think about it carefully, f of x equals any constant times x works. And these are linear solutions. And the question is whether these are the only solutions that you can find for this functional equation. Now, it's more enlightening to start with observing what happens when you work with, say, functions from z to z, with the same property of being additive, functions from q to q. And then we'll think about what happens in the R case, right? So let's say you're working with functions from z to z, which are additive, right? I claim that f of x equals cx, where here c has to be an integer, of course. Is the only solution. You could also make it a function from z to r and make c any real number, but sure. So any ideas how you can prove that this is the only solution for functions from the integers?
This can be proved by induction.
Yeah, right. So the point is that this c is really like controlling what the value of f of 1 is. So you know that f of 1 is equal to c. And the point is that from here you can tell what the value of f for every natural number is, right? So for f of 2, you know that it's f of 1 plus 1, which is f of 1 plus f of 1, which is equal to 2c. And similarly, you can prove that f of x equals cx for all x in the natural numbers. For now, my natural numbers don't include 0, but perhaps I'll replace them with positive integers to avoid controversy. But yeah, so this proves it for the positive integers. And then you have to prove a little bit extra for showing that f of 0 is 0. So how would I show that f of 0 is 0 for like any of these solutions?
So we just put x equals y equals 0, and we get f of 0 equals to f of 0, and that's only possible
Right.
with 0.
Exactly, right. So f of 0 is f of 0 plus f of 0, and that implies that f of 0 is equal to 0. And then from here, if I wanted to prove something like f of negative 3 is negative 3c, I can just observe that this is
replacing x and y by 0. Replacing x and y by 0, we get the value of f of 0.
Right. Yeah. And how would I find f of negative 3? So now we know that it holds true for all non-negative integers, and then I want to extend it for all integers. So any ideas here?
Putting x as -1 and y as +1, then we get the value.
Right.
By using
Right.
the
So
fact
for
that f of 0 is equal to 0.
Exactly. Right. And we already know that this is equal to 3c. So this must equal minus 3c. Right? And the same argument holds true for any negative integer as well. So this is indeed true. Now let's say we are instead focusing on functions from the rationals to the rationals. We know that this is the same argument tells you that f of n equals c times n for some fixed rational c and all n integers. But now I'm claiming that this also holds true for every rational number. So there's like something a little bit more that you have to do here. So let's say I'm looking for f of half. How do I find f of half from here?
Put x and y as half and you get it.
Right. So f of half plus f of half is equal to f of 1, which is c, which implies that f of half equals half c. And it shouldn't be too hard to see from here that f of x equals cx for all x in rational numbers, because the point is any rational number is going to have some integer some positive integer that when you multiply to the rational number becomes an integer, right? So you can kind of clear the denominator using an argument like this, and you can evaluate the function of the rational number as well. So we see that once you've given the data of what f of 1 is, you automatically determine what value f takes at its rational multiples. And when we study the reals to reals, this still holds true. So f of x is, I can determine what f of qx, where q is a rational number. This exact same argument tells me that f of qx is qf of x. Right? And also remember that f of x plus f of y equals f of x plus y. So this is what you would call a Q linear map. So it's not just additive, but it also behaves well with respect to multiplying by rational numbers. But it seems like this is all the data you have. So if I try to extend the same argument, I'm not going to get anything else. I can get that f of so I can get that f of q is equal to c times some constant c times q for all rational q. But I'm missing almost all the real numbers, and there seems to be no clear way in which I can tell you any more values. So perhaps before we proceed with the real numbers, it's a little more illuminating to see what happens in the case of something like q adjoint root 2. Q adjoint root 2.
He has to be an integer or any real number. C.
C. So here C is any real number. So C was only constrained by what the codomain of our function was. So if I'm instead looking for functions from, or let me say q adjoint I to q adjoint I, so every element here is some rational number plus some rational number times I. And I know that f of q is equal to c times q, where c is in like q adjoint I.
What is
Can you please
Q of
repeat
I?
what's Q?
Sorry, what did you ask me to repeat?
What is Q of I? That domain.
Oh, Right. Thank you for checking that. So Q adjoin I is like, so every complex number is a linear combination of 1 and I with real coefficients. Right, you can write it in this form, A plus BI. Q adjoin I is just the subset of these numbers, which are of the form A plus BI, where A and B are specifically rational. And you can check that, multiplying any two elements in Q adjoin I doesn't just give you a complex number, it gives you a complex number in Q adjoin I. Similarly, you can add, you can subtract, you can do all the good stuff you want. It's a field.
But weren't we working on real numbers here for f?
Yeah. So I mean, you can replace I by square root of 2, but yeah, it doesn't matter too much, at least for now. But I wanted to first give an example of what happens in the case of Q adjoin I. But yeah, if you want, we can replace the same thing by Q adjoin root 2, in which case it's just going to be linear combination, some rational number plus some rational number times root 2.
Oh, okay. So I isn't complex here.
Well, for this example, I thought that might be more familiar. Something with I, but in fact, let's
Okay,
just work with root 2 then. So then this would just be a linear combination of 1 and root 2, rational linear combinations. Notice that like such a number is like uniquely determined by the Q1 and Q2. And the Q1 and Q2 are also unique because root 2 is irrational. So we've determined what the function is on all rational numbers, but there doesn't seem to be enough data to extend this furthermore. And you can see that if I in fact tell you f of 1 is equal to some c, and f of say square root of 2 is equal to some d, you'll always be able to extend this to a Q linear function. Given by f of q1 plus q2 root 2 is equal to cq1 plus dq2. So somehow this data of the fact that the square root of 2 is actually the square root of 2, its square is 2, doesn't really matter when you're working with Cauchy functions. Right? It's just treating this square root of 2 as some extra component of Q. So the point is that this is just abstractly, it's like a two-dimensional vector space over Q. And you have like a two-dimensional family of solutions, but technically if you're thinking all over Q, these scalars are also inside Q adjoint root 2. So they are instead like two-dimensional in nature, which means that this map would really be given by some kind of 2x2 matrix, where this would be like the coordinates of C, this would be the coordinates of B. Right? In other words, we're just saying that the linear maps from Q2 to Q2 are like 2x2 matrices, if that makes sense. But if it doesn't, it's not too important.
I'm sorry, but I don't know what linear maps and matrices actually are. I haven't
Yeah. So it's not too important, but yeah, this makes sense, right?
Yeah.
Yeah. All right. So it's the data of a map that's like a Q linear, that's additive and commutes with like multiplication by rational numbers, which kind of follows from this. So it's really just like an additive map. Is going to be given by just the value of f of 1 and f of root 2. And now if I'm looking at functions from the real numbers to the real numbers, right? The same thing holds true as long as I'm trying to extend the map further and further. So I can say that f of 1 is equal to some constant then I can say that f of root 2 is equal to some other constant, because root 2 doesn't lie inside the Q span. It's not a rational linear combination of 1. So you can like define f of root 2 independently. But then what about root 3? Well, root 3 is not a rational linear combination of 1 and root 2, right? That's a good exercise. It's slightly stronger than saying that root 3 is just irrational. So you can give this an independent value as well, and so on. But the question is, what does so on mean, right? Like I can do this in like some sort of arbitrary manner. I can like say define this next for pi, because pi is not a linear combination of a rational linear combination of any of these three things. So I can define f of pi as some C4, right? But I can never stop this process in a finite amount of time. So for instance, if you think about it, just like the square root of all prime numbers, this set has infinitely many elements, and it's all like rationally independent. As in, like, there's no rational linear combination of any of these that's 0 except for the trivial one. Which means that, you know, this process certainly can't end in a finite amount of time. So how do you really give the data of this function? And do you know whether this process can like actually be concluded to give an actual function, right? How do I know that I can extend this process indefinitely? So something that's really useful here is the axiom of choice. But the version I'll be using is Zorn's lemma. So Zorn's lemma tells you that if you have some partial order on a set, so which basically means that it's a set with some notion of, like, you know, what it means to be lower than, so less than or equal, and it satisfies, you know, the properties that you would usually expect. So you have anti-symmetry. So if two elements are like less than or equal to each other, then they are equal, and it's transitive. Right? And you have this extra hypothesis that if every chain has an upper bound, then the conclusion is that there exist maximal elements.
Okay, can you also explain partial order?
Yeah. So partial orders are, you know, it's the data of a set with some order, like some less than or equal to sign. So it's a relation such that, you know, you have anti-symmetry. So if A is less than or equal to B and B is less than or equal to A, then, you know, they're in fact equal. And you also have this transitivity, right? So if A is less than or equal to B and B is less than or equal to C, then A is less than or equal to C. This relation has, in general, it may have nothing to do with, you know, the normal less than or equal to that you have for, say, real numbers. But it is like derived from such a notion because, you know, for instance, R with the less than or equal to sign is a partially ordered set. So is the notion of a partial order clear?
Yeah.
All right. So what do I mean by this claim? Well, I really mean there are like three important words here. What's a chain? What's an upper bound? And what are maximal elements? A chain is some subset of S where any two elements are comparable. So before we proceed, I should say, you know, Why is this a partial order rather than a total order? Because unlike in the case of the real numbers, you could also have an example of the power set of some, say the power set of, I don't know, the natural numbers with the inclusion sign. This is a partially ordered set. So, if some set A is contained in a set B and a set B is contained in a set C, then A is contained in C. And similarly, if A and B are contained in each other, they must be equal sets. But it's not true that you can compare any two sets. So for instance, if I give you 1, 2 is a set and 3, 4 is another set, right? The inclusion doesn't occur either way. So it may not be true that you could compare any two elements. A chain is a subset of S where you can, right? So there is some notion of like smaller to bigger, which applies to all elements. So for
So when
instance,
talking about that Fn, we can actually not compare the elements but the cardinality of the set.
right. So the problem with sorry, excuse me. Sorry, I seem to be coming down with a bad cold, but yeah, the problem with using cardinalities instead is that, yeah, you do get a way to compare sets, but it doesn't satisfy one of these properties. So it is certainly true that you have transitivity of cardinalities because you're just comparing the sizes of their sets, but the anti-symmetry property doesn't hold true. So for instance, if we consider two disjoint sets of size 2, they are both less than or equal to in the sense of cardinality, but they are not equal sets. So it wouldn't be a partial order.
Yeah, so I had a question actually.
Yeah.
Yeah, so when we're talking about assigning values to irrational numbers, how do we know which irrational numbers to choose? Because obviously there exist irrational numbers which
Yeah.
are linear combinations of irrational numbers. And like we can definitely choose some random number like 0.01001001 and we don't exactly know if there exist irrational numbers which are a linear combination of that number and something else, or if that number itself is a linear combination of two other irrational numbers, and if we have already counted them and then we can't count that separately. So it's kind of the additive
Yes.
structure of irrational numbers is pretty tricky. So
Exactly.
yeah.
Yes, it is tricky, and there was no reason I needed to have chosen root 2 first, root 3 second, or pi third. It's all completely arbitrary, right?
Okay.
But this is why Zorn's lemma will help.
Okay, yeah.
So we'll see what the purpose of Zorn's lemma here is. So
Okay.
I've put this on a pause for now, but we'll pick up from there after we know what Zorn's lemma is. So, is the notion of what a chain is understandable? All right. So what is an upper bound? So if you have some subset T in S, X is an upper bound. By definition, if for all T in the set, you have T less than or equal to X. So it's, what do you think an upper bound should be? So this element has to be in S, of course. And a maximal element of S is some element X in S such that there does not exist some Y in S, where X is like strictly less than Y. Strictly less means less than or equal to and not equal to. So it's not necessary that a maximal element has to be unique. So for instance, if this is my poset, where, if I draw an arrow from down, the element up is like greater than or equal to the element down. So this is an example of a partially ordered set where you don't have a unique maximal element. Another example would be like subsets of the natural numbers of size at most 10. Right? So any subset of size 10 would be a maximal element, but it doesn't mean that there's only one maximal element. Yeah. Did someone want to ask a question?
Can you please repeat what maximum element is? I could not catch up.
Yeah, a maximal element is some element of S such that there's no element that is strictly greater. Does it make sense?
Okay.
So for instance, if your poset is the subsets of the natural number of size at most 10, then any subset of size 10 would be a maximal element. Right? If your partially ordered set is all subsets of the natural numbers, then there is a unique maximal element, and that would be the set of natural numbers. But if your partially ordered set was just finite subsets of the natural numbers, there is no maximal element, because you can always make a finite subset of the natural numbers a bigger finite subset, like a strictly bigger one, by just adding some natural number to it. Yeah. Did someone want to ask a question?
You told that maximum element can't be unique, but for example, there are two maximum elements. Wouldn't the two maximum elements be equal because they are the maximum?
So first of all, not that it can't be unique, it may not be unique. So for instance, in the case of just all subsets of the natural numbers, there is unique maximal element. It's the natural numbers. The reason why, so this goes back to the fact that it's a partial order, right? So two maximal elements, if they're distinct, then they will certainly not be comparable, because if they were comparable, then one of them would be greater than the other. The point is that they may not be comparable. So in this diagram, right, if I label these A, B, and C, so A is greater than or equal to C, B is greater than or equal to C, but there is no relationship between A and B. Right? You just can't compare them in neither of them are less than or equal to the other.
Can you give
Which
an
means
example?
that they're both maximum.
Can you give an example?
Oh, so this is an example, right? So this set A, B, C with A is C is less than or equal to A, and B is C is less than or equal to A, and C is less than or equal to B. This is an example. Another example is the subsets of n of size less than or equal to 10 with inclusion. Because any subset of size, the maximum elements would be the subsets of size 10, but that doesn't mean that any two you never have any two distinct subsets of size 10 be included in one another. They're just not comparable. But there's no element greater than them. You can't take their union or anything, because that would not be a subset of size less than or equal to 10.
Okay.
Does it make sense?
Yeah, a little, but okay.
So let me try to give another example. So for instance, the real numbers has the set of real numbers has no maximal element, because for any real number that you give me, there's always a bigger real number that I can find, right? So 10 would not be a maximal element because you have 11.
Yeah.
11 would not be a maximal. Yeah.
Got it.
Okay, good.
So no, I'm asking that if C is comparable to A and C is comparable to B, how can A and B be not comparable? Like that's idea is not making sense to me.
So for instance, right. So let me just write this in an example. So consider the empty set, the set 1, the set 2. and the partial order is inclusion. So there's precisely this poset. So the point is that this is contained in this and this is contained in this. But these two sets, they are not strictly contained in any other set in this in S. But that doesn't mean that they are comparable themselves.
Oh,
Right? Because neither of them are included in the other.
got it, yeah.
All right. Yeah, thank you. So
But if there is one more element, a set 3, 4, then which will be the maximum element?
but that's a great question. So if you had like this, then all three of these would be maximal elements, even though this one is like bigger in cardinality than this, because the cardinality doesn't matter here. All you're thinking about is inclusion.
Yeah, like once you tell like suppose we have 5, 1, 2, 3, and then we have 3 and 4. So are all the 4 maximum?
Yes, that's also a good question. So if I had 1, 2, 1, 2. Wait, so do you mean something like this?
No, I meant 3 is a different set.
So like this?
Yeah.
Right. So then this is not a maximal element because it's contained inside this.
Okay.
So this is not a maximal element, and certainly this is not a maximal element, but these are.
Okay, so in this one, the 3 is contained inside that. So how it can be maximum? Like 1 for 1, 2, 3, or 3 for 3, 4. 3 is contained inside 1, 2, 3, right?
Yes, but not the entire subset. So what it means for A to be contained in B is that every element.
Oh, every element. Got it.
Right. Yeah, so that's the notion of a maximal elements and upper bounds. And the point is, if every chain has an upper bound, then you have maximal elements. So perhaps non-examples are easier to think of first. So if you have the natural numbers, or the real numbers, you don't have maximal elements. But that's because not every chain has an upper bound. In fact, the entire set S is a chain. Right? So we're basically saying that it's somewhat tautological here. Another example is, say subsets of the natural numbers of size less than or equal to 10. Right? Here you indeed, like every chain indeed has an upper bound because if you could have some chain. Let's say that the chain is like strictly increasing. There's only up to a certain point to which the chain can increase, right? Because the cardinality can increase by 1 at each step, but you can only increase the cardinality to at most 10. So the chain has to in fact be finite. And you can just take the largest element of the chain, right? Any finite chain has a maximal element surely because you can just take the biggest element of the chain. There's only infinite chains which are confusing. Does it make sense?
Got it.
Yeah.
So the reason this is did someone want to ask something? All right. So the reason Zon's lemma is relevant to our setup is because so we were choosing these elements 1, root 2, root 3, and pi arbitrarily. You can think of them as this set of sets of real numbers, subsets of the real numbers, which are Q linearly independent. Basically, they don't have any non-trivial rational linear combination that's 0. So for instance, 1, root 2 would be an element of S. So would 1, root 2, root 3, or say just root 2, or technically the empty set. But something like 1 and 3 would not be in S because something like 1 and 3 would not be in S because you have like 1 times 3 plus 3 times -1 is equal to 0. Or something like 1 root 2, 1 minus root 2 would not be in S.
By linear combination, you mean some integral multiple?
So it's equivalent to have a linear combination with integral multiples and rational multiples, a non-trivial one, to be 0 because you can always just clear denominators.
Ah, okay. I was thinking that why are not like 1 times 2 minus 2 times 1 times 2 plus root 2 times minus root 2 will be still 0. But it's not
Oh,
really
yeah. So yeah, it's all over Q.
all over Q, right?
Right. And now we see that, Zorn's lemma, this is indeed a partially ordered set. And Zorn's lemma applies here because every chain indeed has an upper bound. So what's a chain here? It's just going to be, some subsets. So a chain technically need not even be countable, but what I'm going to say still applies for like uncountable chains. The point is, if you have any chain of subsets of rationally linearly independent sets, then their union is also an S. And certainly that would be an upper bound if it were an S. So why is it an S? The point is that if you take any so assume that this union is not contained in S, right? Then there would be some elements alpha 1, alpha 2, say so on till alpha 10 in the union, which are not independent over Q. And there can only be finitely many. Because what it means to not be independent is you're saying that some non-trivial linear combination of them is 0.
Could you just again explain this part from C1 belonging to C2?
Right. So I'm saying that this, if this is not an S, then there's you can find finitely many elements which have a non-trivial linear combination. That's what it means for an infinite set to be, to have Q independent elements.
Oh no, like first of all, C1 that is a subset of sign, right? Which all along C1 subset of C2. You're muted.
Oh, sorry. Yeah. So the point is that C1, C2, so on, that's an example of a chain. So I'm considering a chain and I'm showing that it has an upper bound.
Okay, and also that UCI means a union of CI, like what's U like in this one?
Union. Yeah.
Okay, got it.
Right. So if this were an S, then it's certainly an upper bound, right? Because the partial order was inclusion. Right. So any CI would be contained in the union of all the CIs. So the question is whether this is in S. And the point is that, if it were not, then there would be like some non-trivial linear combination that's 0. But the point is that a non-trivial linear combination can only have finitely many terms. Right? So if I were to take like some C1 which contained the alpha, okay, it may not be the same C1 here, but let's just say without loss of generality that this is contained in C1, so on till the alpha 10 is contained in C10. You can just take the biggest of these CIs. There are only finitely many of them, and they're in a chain. So there's a biggest one of those 10. And if you just take the biggest one of them, it's going to contain all those alpha i's. But that would imply that C10 itself is not a set of independent elements because all these alpha i's are in C10. And C10 is certainly independent. So you cannot have a linear combination of this kind. So the point is that, being like Q linearly independent is somehow a sort of finite constraint, which is what allows you to do some union of this sort. Does it make sense? Any questions? All right. So the point is, because of that, you can use Zorn's lemma to find a maximal element of S. So it's just basically like some maximal subset of the real numbers which are Q linearly independent. And you can show that for such a subset S, any rational number, any real number is like a unique linear combination of elements of that kind. And now that you have such a maximal element, and you've expressed every real number as a unique linear combination, you can just say that a function which is additive on the real numbers is the same as just some set theoretic function from that set to the real numbers. So it's somewhat of a pathological thing to say because all the maximal elements of S are really weird. Like you can't give me, you can't actually write down any maximal element of S, which is like one weird part of it. And the other weird part is that the function is going to be absolutely funky, right? And that's kind of displayed by the fact that, even if you put some mild hypothesis on the function, say the function is continuous, then it would automatically rule out all these functions except,
Yeah, I still don't understand what does a function mean when it is continuous. Like, what is it actually? What is continuous?
So the informal definition is just that you can like kind of graph it without raising your hand. Basically, it means that close by points in inputs, map to close by points in outputs. The formal definition is probably slightly more technical, but what you're basically saying is, it's I guess a good way to think about continuity is somewhat like in physics. So let's say that you want to measure some length, right? And let's say that you want to measure that length with, some, I don't know, within some error. Let's say I want my error to be less than 0.05 centimeter or something. Then you take an appropriate instrument to measure within this error, right? And continuity is somewhat similar in the sense that, if I have some function and let's say f of, say, pi is equal to 3, then what it means for f to be continuous at pi is saying that, as long as, so I can't really measure the function at pi, but I can try to measure it really close to pi. And the point is, if you are sufficiently close to pi, so if x is sufficiently close to pi, then f of x is going to be 3 plus some error, and this error will be less than, you can like preset what the error is going to be. Say the error is 0.05. Then you can make sure that the error here, but what the value of f of x is just going to be 3 plus some small quantity. And that small quantity is going to have magnitude less than 0.05. So what is sufficiently close? Sufficiently close might be x has to be, very, very close to pi or something, right? And this is what it means to be continuous at pi. And to be continuous as a function means it's just continuous everywhere in your domain.
Okay, got it. So, I guess you told that for a continuous function, the Cauchy-Zephyr holds f of x equals cx, right?
Yes.
So, I wanted to ask that. Sorry.
Yeah, go on.
Yeah, I wanted to ask that what difference does a continuous function bring, and what if the function is discontinuous? What will happen to the Cauchy-Zephyr?
Yeah, so the discontinuous functions have these kind of pathological solutions where you just like choose a maximal element that's like a basis, and you just like define what it is on each basis element. It just like magically makes it a function on the real numbers. So that's kind of pathological. But the point is that if you know continuity, we were already done before. So we already knew what the function is at the rational numbers. But every real number can be approximated arbitrarily close to a rational number. So you have to like fill in the gaps only the natural way. So I don't want to elaborate too much on the formalism of why that holds true. But it has to do with the fact that the rational numbers are dense in the real numbers.
Got it.
Right. So I guess at least intuitively that kind of makes sense, right? So you basically told what the function is at every rational number. And the point is that you can find these rational numbers almost they're like spread out all throughout the real number line. So there's only like one way to fill in a continuous function after you know it just on the rational numbers. Of course, it may not be possible to fill in that function, but you already know how to extend this to all the real numbers as well. It's just the same linear function. All right. So that being said, let's try to solve some problems. Not sure which one of these I want to do first. Let's actually do this one first. So yeah, I'll give you a little bit of time to think about it. Yeah, hello.
Yeah, so first of all, the Cauchy functional equation is given. What my idea is that, first of all, the Cauchy functional equation is given. That means the function, we are considering the function to be continuous. And we are telling that f of x equals cx works from the Cauchy functional equation. Now, if we plug in f of x equals cx in that second one, first of all, if we see that, if we plug in f of x equals cx, I guess something can happen. Like we will get f of cx to the 2013 equals c to the 2013 x to the 2013 to x to the 2013 x to the 2013 cancels. So c becomes 1 or 0, I guess. And I guess like that we can solve.
Oh, you're talking about the problem. Okay, that makes more sense. So yeah, let's get started. Yeah, so yeah, the problem is that f need not be continuous. So although Cauchy's functional equation admits like pathological solutions, your like this additional constraint of x of f commuting with 2013th powers may make sure that there are no pathological solutions anymore. There are only nice solutions. But it's still worth checking. As you said, among the functions, among the linear functions, which satisfy Cauchy's functional equation, which ones work? Right? So as you said, if f of x equals cx, then f of x power 2013 is equal to c times x power 2013, and f of x power 2013 is going to be c power 2013 x power 2013. And these must be equal always.
Yeah. So we can just cancel out x to 2013 or x will be 0. And if we can cancel x to 2013, we can say that c is 1 or 0. Like, no, we can't say c is 1 even. Yeah.
Yeah, let's be a little careful about that. So you can certainly just plug in, say, x equals 1. Anything that's not 0 and cancel out x by 2013. So you indeed must have c to the 2013 equals c. But what does it imply about like the values that c takes?
It's 1 or 0.
It can be -1 too.
right? It can also be -1 because the parity is like all correct. But
Yeah.
certainly no other values, right? Because it's 0. If it's not 0, then you have C power 2012 equals 1, and the only elements with finite parts that are 1 in the real numbers is like, they're 1 and -1. Yeah. So you know that f of x equals x works, f of x equals 0 works, f of x equals -x works. You already have these 3 solutions. And the hope is that, these would be the only solutions, because these are the only solutions among the nice ones which satisfy Cauchy's equation. And you're going to hope that the pathological solutions, which are just like absolutely pathological, of course, don't satisfy this extra nice hypothesis. Right. So yeah, any ideas about how to proceed?
By the way, like if we just start normally using that only thing f to the, like here we just check that what works. So if we just start normally that f of x equals x to the 2013 equals f of x to the 2013, we can plug in x equals 0 and check. But will that work? Like normal solution, if we see, we can, if we plug f equals 0,
Yeah.
we get f of 0 is 0.
Yeah, but you can get that from just Cauchy's functional equation as well. So yeah, you do know that f of 0 is 0.
Okay.
I think we can prove that the point 1 in the domain is continuous for any f that satisfies by from f of 1 being equal to 1 and f of 0 being equal to 0.
I'm sorry, I don't think I caught that. Could you repeat?
So since if we substitute x equal to 1 in the second relation, like f of x whole
Yeah.
power 2013 is equal to f of x whole power 2030. Yeah, so
Right.
we'd get a trivial solution is f of 1 equal to 0 or f of 1 equal to 1. So if we
Or
then
minus
notice that is, yeah, sorry.
Yeah, so note that the C is equal to f of 1, right?
Yeah.
Here, but it's the same argument. So like this implies that f of 1 must be 1, 0, or -1.
Yeah, so that's fine. So, but also from the Cauchy's function equation, you can prove that f of 0 is equal to 0. So if you take any then the neighborhood of 1 in the domain like 1 plus delta and 1 minus delta, then f should be continuous at 1.
No, so f need not be continuous. So we're not saying that it's a continuous solution of Cauchy's functional equation, because if it were, then we would already be done. We already know which linear function.
I'm not saying f is continuous at every point in the R, just at 1.
Yeah, why is it continuous at 1?
So you can take any the neighborhood of 1, so like 1 plus delta and 1 minus delta. And then
Right.
f of 1 plus delta would be equal to f of 1 plus f of delta. And as delta
Yeah.
tends towards 0, f delta would tend towards f of 0. And since f of 0 is 0, it should be f of 1.
No, but when delta tends towards 0, why does f of delta need to tend towards 0 as well? Because that assumes that f is continuous at 0, right?
Oh, I see the contradiction. Okay, thank you.
Right. So yeah, so I should say, so for Cauchy's functional equation, if you know that it's continuous, then you know that it's linear. But in fact, if you know that it's continuous, if you know it's continuous at any point on the real numbers, it's still going to be like a linear function. So that's how pathological these solutions for Cauchy's functional equation are, like except the linear ones, of course.
Yeah, so
This
I
is
mean
like
the
absolutely ridiculous.
Yeah, so the solution definitely, I mean, I think it's fair to claim that there's a certain class of irrational numbers which can be assigned something in this problem, but I just don't know how to find that
So
class of irrational numbers.
I just
yeah,
thought
this
of some-
hypothesis. Yeah, go on.
Yeah, if I was to hypothesize, then I can definitely say that the 2013th root of every prime can be assigned something. I think. I don't know.
Yeah, you are. Yeah, so like you can certainly say that f of 20, say 2013th root of something like 5 would
Yeah,
be so the 2013th root of f of 5,
yeah.
if you want 5 times f of 1. And 2013th roots
Oh,
make sense because you're working over the real numbers.
yeah.
So yeah, you do have things like this.
Okay.
So this is how you know that you get something slightly more than what Cauchy gives you, because originally we wouldn't have been able to figure this out in terms of f of 1. So here's an idea. So let's say you have f of x bar 2030 equal, that this is equal to f of x bar 2030. And if I consider f of x plus 1 bar 2030, this is going to be f of x plus 1 bar 2030, which in turn becomes f of x plus f of 1 2030. Right?
Oh yeah, right. Because we have the Cauchy, right?
Yes. So think about what you can say from something like this.
Can't we apply induction? For like, if we have to just find for integers for now to check if this works, can't we just apply induction?
We're not just trying to find what it is over the integers here.
Yeah, no, like my idea was that if we find a general trend over the integers and we find that this is something that the discontinuous Cauchy does not explain, we can just claim it's continuous. That's what I was telling.
So how would you prove that it's continuous?
No, I was like, if we find a general trend of solutions for the integers, like x ranges of the function ranges of integers, and we find something in the general trend that we can claim that the discontinuous Cauchy does not support, then we can say that the function is continuous. That's what my idea was. May not work.
So thing is, if you try to work out what it is over the integers or whatever, you won't see any of the pathological nature, because all pathological solutions to Cauchy's functional equation still look nice if we just restrict them to, say, the rational numbers or the integers.
Oh, got it.
All right. So we know that f of 1 is like 1, 0, and minus 1. Let's think about the case where f of 1 is equal to 1 for now. And let's prove that f of x is equal to x. So you get that this is equal to f of x plus 1 par 2030. So, this might have some expansion like f of x par 2013 plus 2013 times x par 2012 plus so on till 1 equals the same, but as a polynomial of f of x instead. So if I look at this equation and this equation, and I subtract 1 from 2, then I'm going to get that f of 2013 x par 2012 plus so on till plus 1 equals f of x, sorry, 2013 f of x par 2012, so on till plus 1. So we've taken this difference of the polynomial at x plus 1 and the polynomial at x, they get a polynomial of lower degree where the f commutes with the polynomial, in the sense of, if you take the polynomial of x and then apply f, that's same as taking f and then applying the polynomial.
Oh, wait a second. How did you like just subtract? Like if you did f of what you did was f of x to the 2013, and you in the right R in this RHS it was f of x to the 2013 plus something. How did you just subtract between the functions?
So that's where the additivity comes to nature, right? Because in f of x minus f of y is just f of x minus y.
Oh, okay, got it.
Right. But I can repeat the same trick to get f of some degree 11, degree 2011 polynomial. I'm not saying all, just like some polynomial that I don't want to work out is equal to the same polynomial of f of x. Does that make sense? So like I can repeat the same trick. If I call this polynomial p of x, I can work with p of x plus 1 minus p of x, and that will be like a degree 2011 polynomial. And then I can do the same trick again to get some degree 2010 polynomial, and so on till I get some degree 2 polynomial. Does
Can
that
you
make
figure
sense?
out that degree 2 polynomial though?
You can, but it's not particularly important to the problem. So let's say that the polynomial, say it was 10x squared plus 23x plus 99. It's not, but let's just say it won't matter for the argument we're going to make, right? So you have something along the lines of f of 10x squared plus 23x plus 99 is equal to 10 f of x squared plus 23 f of x plus 99, right? But now this side by Cauchy, like the Cauchy constraint becomes just f of 10 f of x squared plus 23 f of x plus 99. Does it make sense? So I split it into f of 10x squared, f of 23x, and f of 99. And then you already know that f of any, because you know f of 1 is equal to 1, you already know what f of any integer is. Is that good?
Yeah, got it.
All right. So yeah, these two are equal. And then these terms are the same. And then you can cancel out the 10 as well. So you get f of x squared equals f of x squared. And I will not need it, but I'll let you think
Just a
about
second,
why
can you just repeat? Sorry.
Yeah, where do you want me to repeat from? So from here?
Yeah.
Right. So I take, the equation I have. So f of this polynomial, this quadratic, is equal to the quadratic of f of x. So this is equal to 10 f of x squared plus 23 f of x plus 99 by Cauchy, the Cauchy constraint, because I can just kind of split this polynomial up. And then these terms are like all the same. The linear and the constant term are all the same. The only difference is that in the quadratic term, where here the square is inside the function, there the square is outside the function. Does it make sense?
Wait a second. How do you get that f of 10x squared plus 23x plus 99 equals 10 times f of x squared? Like
Right. So yeah. So you agree that this is equal to f of 10x squared plus f of 23x plus f of 99, right?
Right.
And we have assumed for now that f of 1 is 1.
Okay.
So then f of 99 is 99 f of 1, which is 99. This is f of x plus f of x plus so on 23 times. So it's 23 f of x.
Okay, it's the same thing.
Yes, just the standard Cauchy stuff. Is that good?
Yeah.
Right. And from here, you see that f of x squared is f of x squared. And I'll let you think about why this is true. You can extend this argument to show that f of any polynomial of degree at most 2013 is the same as, the same polynomial of f of x. And in fact, you can also extend that to like not just bounded by degree 2013, but all degrees, because you can like kind of repeat. You also know that f of x bar 2013 square is equal to f of x bar 2013 square. But yeah, it'll not be particularly relevant to what we are going to do right now. We'll only need this constraint. So the point that this gives you is that x square can really be any non-negative real number. And the right side is a square, which means that it's a non-negative real number. So you see that for all x greater than or equal to 0, f of x is also greater than or equal to 0. Right? So is that clear?
Yeah.
And this is good because it's already giving us some notion of continuity or whatever. So now I claim that from this constraint, f is increasing. Perhaps I'll say f is, I'll say non-decreasing. So do you see why f of x is f is non-decreasing? So is everyone familiar with what non-decreasing means? If not, I can clarify.
It's either constant or increasing.
If you think about it using a graph, yes, but remember that f may not be continuous. But yeah, that's right. So yeah, does anyone see why f has to be non-decreasing? That is like, if f of x is, if x is less than or equal to y, then f of x is less than or equal to f of y. So let me give you a small hint. Oh. Yeah. So you know that x plus z is equal to y, where z is like non-negative. So f of x plus f of z is equal to f of y by the Cauchy condition. And we know that this is non-negative. Which tells you that f of x is less than or equal to f of y. Does it make sense?
Like by Cauchy, right? But
Right.
Yeah.
All right. So now f is non-decreasing, but you also know that f of x equals x at all rational numbers. And I claim that these two facts combined tells you that f of x equals x. And it's because like if you have some, let's say that f of e is equal to pi, for instance, right? Assume for the sake of contradiction that you have some number which for which f is not this the identity. The point is that you know there's some rational number between e and pi, right? In fact, you have 3 is between e and pi. So some rational number is strictly between them. Then you have f of e is less than f of 3, and this was pi, but this was 3. So you have a contradiction. So basically, the fact monotonicity gives you, it doesn't technically give you continuity, but it helps you as much as continuity, perhaps even more. So this argument in general just shows you that if you have some monotone solution to Cauchy's equation, then it still has to be linear.
By the way, how
Does
was
that make
f of
sense?
e equals pi? Like, did you claim it was?
Yeah, this is the claim. But I mean, the point is e and pi could have just been any unequal numbers.
Okay.
So you cannot have f of x not being equal to x, which means that it's f of x is equal to x.
Okay, so f of x equals h, that means that the function is continuous, right? Yeah, makes sense.
Well, yes, but we've already figured out what the function is, right? So it's going to be f of x equals x for all x and real numbers. And yeah, I mean, yeah, the solution is certainly continuous.
F of x equals x, 0 and minus x also, right?
Oh, this was all in the case where f of 1 is equal to 1.
Okay, so we will have other cases also. Makes sense.
Right, but we'll be quickly done because of that. So the point is, in the case where f of 1 is equal to minus 1, you can check that negative f also satisfies the constraints. Right? Certainly, negative f of x plus y equals negative f of x plus negative f of y. Not much to check there, because you just put a negative sign in the entire equation. And on the other hand, negative f of x bar 2013 is going to be negative f of x bar 2013. And because 2013 is odd, we fortunately have this. And negative f has f of 1 equals 1, which means that negative f must be f of x, must be the identity function, which means that f of x must be negative x. Does that make sense?
Works.
Awesome. Finally, you have the case of f of 1 is equal to 0. Now, if you go back to the argument we had here, right? If I had f of 1 is equal to 0, this would be f of x plus f of 1 par 2013. And that would just be f of x par 2013, because f of 1 is 0. And when I subtracted it, instead I would get that this degree 12 polynomial, instead of being this thing, it would just be 0, because both sides were on the right side were f of x par 2013.
Right.
And if I proceeded all the way, if I did the same argument, I would instead get that f of x squared is equal to 0, instead of getting f of x the whole square the other side.
By the way, by repeating the same process, do you mean that you keep subtracting?
Yes, I do p of x plus 1 minus p of x for whatever polynomial I have, to just
Yeah.
reduce degrees.
Yeah, so how if you're subtracting something from 0, how is it staying 0? Okay.
So the point is, this is, so for the 2012 degree 2012 polynomial, so you have that f of x bar, so let's say it's p of x. I know that it's 0. This is a degree 2012 polynomial. I can instead put x plus 1 and it's still 0. And then when I subtract, because of Cauchy, I can subtract inside. And this is still 0. And now this is a degree 2011 polynomial. Because the leading terms will cancel once you apply. Right. So this process in general is called finite differences.
Also, one second. P of x plus 1, it told me. No, like x plus 1. Like, for example, let p of x be x to the 2013. plus and so on till something, and p of x be like
Yeah.
x will be and the same polynomial.
No. So P was the degree 2012 polynomial. It was the degree 2012 polynomial you got from applying x plus 1 whole part 2013 minus x part 2013. Because
Yeah.
in that case, you had f of x plus f of 1 part 2013, and this was 0.
Yes.
So the right sides were equal. Right. So specifically for that degree 2012 polynomial. Does it make sense?
Yes. Makes sense.
Right. And then if you continue the process all the way, we will get some f of some quadratic. Again, I'm just going to choose some random quadratic. It's not going to be this one, but yeah, some quadratic. And the point is that, and I can apply the same thing one more time. And I'm going to get, in fact, a linear polynomial. Say, I don't know, 100x plus 1000. I mean, I'm just writing some random polynomials, but the point is the polynomial doesn't matter. So you'll get that this is 0. But you know that f of 1000, so this is just 100 f of x plus 1000. Oh, I'm sorry. It's just 100 f of x. F of 1000. Remember, f of 1000 is 0. Because f of 1 was 0.
So f of x
And f of 100x is 100 f of x by, Cauchy. So that tells you that f of x is equal to 0 everywhere. So those are your 3 solutions. Does it make sense?
Yeah, the idea was too much out of it.
Right. So the crucial observation is you have to try to work with finite differences. And somehow this is kind of a forced idea because you have to somehow get some kind of positivity condition, how f of non-negative numbers was non-negative. Because if the same question was something like functions from the complex numbers to the complex numbers, there will still be pathological solutions. Not as pathological, but still pathological. Right. Yeah, but I don't want to talk too much about that.
Also for just for f complex to complex for continuous functions, will it still be f of x equals cx?
I'm sorry?
Like here the domain and codomain are real and real, but if the domain and codomain were complex and complex, would the Cauchy functional equation still have solutions f of x equals cx for continuous f?
For continuous ones, no. I'm glad you asked that. So if you have Cauchy's functional equation from C to C and continuous, so you're kind of eliminating the pathological ones, there are still solutions. I mean, you can say what the solutions are. So you have f of x, f of z, let me write. This works, but in fact, you also have a complex conjugation function. And complex conjugation is also linear. So it's also additive. So you can verify that complex conjugation works. So the reason why you have a two-dimensional family, basically 2 independent kinds of solutions, is because C is R2. It's a vector space.
R2,
basically
right.
it has 2 coordinates of fields, which is why you have 2 coordinates of solutions, even in the continuous case.
Yeah,
Is this the
z
only
is
solution
z is in a coordinate. So and z conjugate means the conjugate of z is also in another coordinate because R2 means 2 coordinates, right?
Right.
So z is in a coordinate and the conjugate of z is in another coordinate.
No, that's not. So I'm not saying that this is the real part and the imaginary part. This is literally the sum of complex numbers.
Okay.
Right.
Though the function is continuous, are there finitely many solutions or?
These are all the solutions. So you can think about why these are all the solutions. It's the same it's all this stuff that we've done till now. So like, you know, the function, the rational numbers, and then you can extend it because of continuity to the real numbers. But once you extend it to the real numbers, you can see that, you know, these are the only two solutions that exist, because C is just like, you know, a linear, every complex number is a linear combination of 1 and I. So, you know, think about what the function takes at 1, think about what it takes at I, and you can determine the function from there. Does it make sense?
But what does continuity mean for complex numbers?
Oh, it still means the same thing, but you know, where magnitudes of complex numbers are taken like as absolute value.
Also, like
So you can think of it as a function of R2 to R2. But yeah, it doesn't matter too much if you don't understand what that means.
okay, one thing, two things actually. The first thing is that for complex to complex and discontinuous, there will be like a different level. Like what type of solutions? Completely pathological.
Yeah.
And the second thing is that for R to R, we know that it's like from function of like a real number to real number. From R square to R square, how will you define it?
What do you mean?
What's R square times R square? Like, can you give us that R square to R square?
I'm not so like C is like R square, but I'm not sure I understand what the question is.
No. Like, I was asking that for example, you have a set from reals to reals, right?
A function, yeah.
Yeah, a function from reals to reals. That means you're taking a real number, plotting it in a function, and you're getting another real number. But
Yes.
now R square, R square, you're plotting it R square in a function, and you are getting another R square number. That's what it means. R square to R square.
Yes,
Okay.
that's right. But you have to be careful about like what plotting means. A general function can't really be plotted in like a classical sense because it may not be continuous. Here it is continuous, but of course, you know, your input space is like two-dimensional, output space is like two-dimensional, and you're not going to draw some sort of four-dimensional graph. So the continuity is really happening like in the abstract definition of continuous, which basically means a small change in the input means a small change in the output.
Good.
All right. I think we might have some time to fit in this problem. I'm not sure. How much more time do I have? Like, would
We
it
can
be
go a
okay?
little bit. uh, Yeah, if people are fine with it, we can definitely go a little bit over.
All right. Yeah. So let's think about this problem, I guess. So I guess for the interest of time, let me
Can you show the
start.
other problems?
Sure. Yeah. Yeah. So the other two problems are about monotonicity. Maybe you can take like screenshots or whatever, or you can just like write the sources. So yeah, one of them is like IMO 2022 P2, and the other one is like the Putnam 2016 B5. Yeah, problem one, I don't really have a source. I made it for the session, so but it's like a generalization of the type 1 TST problem. All right. So yeah, let's discuss this one. So you basically have something along the lines of Cauchy's functional equation, but instead of having like, you know, F, you have like repeated compositions of F, and it's not even the same multiplicity on both sides. So it's kind of weird, but we can still extract something. We can still extract like a kind of classical Cauchy kind of equation here. So the observation you have to make is that, f bar m of x plus y, the point is I can choose any numbers here that add up to x plus y, right? So can you think of another nice set of numbers I can choose that add up to x plus y?
X minus X.
X, I'm sorry, what?
X and minus X.
X and minus x would add to 0, right? So you want two numbers that add up to x plus y.
Like we can say
So you want to choose two numbers such that it gives you like something really useful.
we can say 2x and y minus x maybe.
Yeah, you can. But it
Will not give us
isn't.
useful things.
Yeah, so there's a substitution that gives you something really useful, right? So substitutions like x plus y and 0, right? Because this thing is just a constant. And now you have, if I subtract fn of 0 twice, then I get this. And if I define this function as g, this is g of x plus y, this is g of x, and this is g of y. So g is a Cauchy function. It's a Cauchy function. Does that make sense?
Wait a second, just a second. You're telling me that acha, okay. So it's this side it's minus 2 above there and that side it's okay, makes sense.
Yeah. So the point is this extra constant means that if you subtract some appropriate constant, then the function is going to be like Cauchy. It's similar to how like we have like some linear equation, some linear function with like a constant term. Then you can just subtract a constant to make it linear, which is basically what we're doing. So the point is that fn of x is going to be g of x plus fn of 0. This can be like any constant. Let's call it beta. And g is like a linear function. And remember that f is a continuous function. So g is also a continuous function because it's just f repeated a couple of times, which means that g of x is going to be some constant times x. Does it make sense?
It's a little confusing. Can you repeat once?
Yeah. So is it good? So are you able to understand why g of x is going to be equal to some constant times x? Because like g is the function fn of x minus fn of 0. This is a constant, so and f is a continuous function. So applying it repeatedly still gives you a continuous function.
No, like f of f is a continuous function and f of fn of 0 is a constant, right? So how does that
Yes.
give us g of x equals a constant time x? That's what I'm not able to understand.
Oh, so I mean, we subtracted an appropriate constant so that we have this g of x plus y equals g of x plus g of y relation. So g is like a Cauchy function, and because of this, it's a continuous function as well. And you know the continuous solutions to Cauchy's functional equation. They're just the linear ones.
Okay.
Is that good?
Yeah.
All right. So you know that g of x is going to be some linear function like this, which means that fn of x is going to be alpha x plus fn of 0. And I'm just going to call that constant beta. Right? So you have, so now you know what fn is. But if I plug that into the original equation, I get fm of x plus y equals fn of x plus fn of y equals, this is alpha x plus beta, this is alpha y plus beta. So I get alpha of x plus y plus 2 beta. And of course, now I just have like something in x plus y can just denote any real number. So I guess I can just instead write fm of x equals alpha x plus 2 beta. Does it make sense?
How you totally went from x plus y to directly x?
So x plus y can really denote any real number, right? So for instance, you can choose y equals 0.
Got it.
Right. So these are the two constraints now. We have made our problem equivalent to finding f would satisfy both this equation and this equation. All right. Now, if you read the problem, m and n were relatively prime positive integers, and that will come into play because like a quite important condition. So first of all, you know that fm composed n times is the same as fn composed m times. All these exponentiations are repeated composition, right? So for instance, you know what is fn composed twice? It's going to be alpha x plus beta, but then you apply the same thing again. So it's going to be alpha square x plus alpha beta plus beta. And in particular, the leading term is alpha square. So what's going to be the leading term in fn power n?
Alpha m.
Yeah. Some constant term. And similarly, fm power n is going to be alpha power nx plus some constant. But I guess I really don't need this. So perhaps this is not important. But okay, let me just keep it there. So the point is, let's say I tell you that f3, which is f composed 3 times. No, I'm just writing down an example. M equals 3, n equals 5, let's say. I know that f3 is going to be some linear polynomial, and f5 is linear. The nice thing about linear polynomials so say that alpha is not 0 for now. The nice thing about linear polynomials, which are like actually degree 1, is that they are bijections from the real numbers to the real numbers, which means that they're invertible functions. You can talk about f inverse, right? And that means that, and it's like, all its compositions are linear functions. Its inverse is also a linear function. So you can just like try to play around with like, composing and decomposing these functions. So for instance, f power 5 minus 3 is just going to be applying this function and then this function's inverse.
Is a
Does that make
invertible
sense?
function if f of 3 is like ax plus 2 beta, then is that inverse of f of 3 means that the reciprocal of that?
No, it's this function. The function you have to undo. So like so this is f power minus 3. Because f power 3 composed f power minus 3 is just the identity function.
What's the identity function? Like it has the value
f of x is x.
f of x is x.
Right. So yeah, all the operations here are composition of the functions. Yeah. And in particular, I think like a few lectures ago, you had some, I guess you had Sai lecture about the Euclidean algorithm. And that's exactly what we're going to apply here, right? There's some linear combination of these which is going to be 1 because they're relatively prime. Integers, positive integers. So this is also going to be a linear function, a linear polynomial. Because, you know, composing linear polynomials is still going to be linear, and the inverse of a linear polynomial is still linear.
By the way, a linear polynomial and linear function are the same, right?
So if I say linear function, then I may mean just like no constant term, but I mean linear polynomial here. Like, you know, something like ax plus b.
No, linear polynomial I get. Like what's linear function? Like in your
A linear function, I mean something like ax.
it's like no constant term.
Yeah. But yeah, here I do mean linear polynomial.
Like if you say no constant term, it may also mean ax square plus bx, right? But that's
No, a linear polynomial with no constant term.
okay, got it.
Right. So is this clear?
Yes.
Why f is going to be a linear polynomial? Right. And remember, the problem was not to find f, it was to prove that there is some interval where f is a linear polynomial. And if f is itself a linear polynomial, then it's certainly going to be a linear polynomial on any interval in R. Technically, I guess R itself is an interval, but yeah. So that was the case where alpha is not equal to 0. If alpha equals, and I mean, if you want, you can actually find out all the solutions in the case where alpha is equal to, alpha is not equal to 0, right? So you have like solutions in the form f of x equals x. You have solutions in the form f of x equals minus x. And then there's also this weird solution when m equals 2 and n equals 1, where you have like f of x equals x plus, a constant minus x. In fact, this was the original Taiwan problem. But yeah, it's not important to our problem because we're just like, you know, proving that f is a linear polynomial somewhere. Anyways, so what happens now in the case where alpha is equal to 0? So you know that f composed, say, 3 times is 2 beta, f composed m times is 2 beta, and f composed n times is beta. But then this implies that f composed mn times is 2 beta, and this implies that f composed mn times is beta, right? Because I'm just like applying the constant function again and again, which means that 2 beta is equal to beta, which means that beta is 0. Is that good? All right. And that implies that f composed, say, n times is 0. It also implies that f composed m times is 0, but yeah, sure. We just need one of them. And I claim that if you have a function which repeated a couple of times is 0, then the function must be 0 on some interval. If it's 0 on some interval, then like since a 0 function is a linear polynomial, it's not 1 of degree 1, but it's still a linear polynomial, we'll be done. The claim is f is 0 on some interval. It need not be the 0 function itself, though. Yeah, I'll let you think about like, you know, how you can construct some examples of continuous functions, which, you know, such that say f square is equal to 0, but f is non-zero. It's a good exercise. So you have like a lot of functions of this kind. Anyways, so why does f have to be 0 on some interval? So you know that f n equals 0. So let's say that d is the smallest positive integer such that fd is equal to 0, right? Because I'm giving you some positive integer where its composition is n times is 0, which means that there's a smallest such positive integer by the well ordering principle or whatever. Right? So that means that f composed d minus 1 times is not 0. In the case where d equals 1, d minus 1 be 0, so f composed 0 times is just the identity function. This is like convention, which kind of makes sense. But yeah. So this is not a 0 function, but this is 0. And this is like f composed with f to the d minus 1. But what does this mean? You have f to the d minus 1 from the real numbers to the image of f to the d minus 1. And then once you apply f to that, it becomes a 0 function. Which means that the image of f to the d minus 1 must be completely contained inside the pre-image of 0 under f. Right? So the image of f bar d minus 1 is contained inside the pre-image of 0 under f. And since f is sorry, yeah. So first of all, is it clear that f of 0 is 0? So perhaps I should explain that first. So first of all, why is f of 0 equal to 0? Because if we had yeah, so if you have like f of 0 not equal to 0, then the problem is that, let's say f of 0 is equal to, say, 10, for instance, right? Then you are given that, say, f to the n is the 0 function. Then f to the n plus 1 would have image ten, and then f to the n plus 2 would have image 0, and so on. But the point is that you know that f to the f of 10. But you know that f to the 2n is again 0 because f to the n composed with f to the n. So the point is that you can eventually find out that f of 0 is equal to 0 from this argument. And so this image contains 0, but it also contains some other number. Because the f to the d minus 1 isn't just a 0 function. But if it contains two numbers, since f to the d minus 1 is a continuous function, it contains all the numbers between them by the intermediate value theorem. And that whole interval has f being 0 because it's all contained under the pre-image of 0. Does it make sense?
Like, could you repeat the last part once?
Yeah. So now that you know that image of f to the d minus 1 contains at least two numbers, say it contains, for example, 0 and 10, it must contain the entire interval between 0 and 10. Because f to the d minus 1 is a continuous function, right? So if it takes some value 0 somewhere, it takes a value 10 somewhere, it must take all the values in between. And in all those values, f is 0 because this image is contained inside the pre-image of 0 under f. Which means that in this entire interval, f is 0. Does it make sense?
Yeah, now it makes sense.
All right. So yeah. Yeah, I think that's probably a good place to start.
Thank you so much. This is a very fun session.
Very
Thanks
you.
a lot.
Very nice. Enjoyed a lot.
All right. Yeah, I have to see the match now, so I'll be gone.
Yep.
See ya.
Bye. Thank you. Have a nice day.